So welcome everyone. Today we're glad to have Dougal who will speak about Hodge theory and representation of forces.
Right, thank you. Thanks for the introduction and for the opportunity to visit here. I would say I'm having a good time. Of course, the weather, maybe not so much, but certainly the place of people. Okay, so I should maybe, of course, start with a slight apology that this is supposedly an arithmetic geometry seminar, and maybe there will be very little arithmetic in this talk, and maybe a fair amount of representation theory. So I hope at least some of the words, maybe Hodge theory, depending what sort of arithmetic we're talking about, real groups, might at least be of interest to people. So, and for that reason, also, if anything, I'm assuming doesn't make sense, please interrupt, ask questions. Yeah. Okay. So let's start. So what I want to talk about is a story about, it's about Hodge theory and representations of real groups. Maybe it sort of starts motivated by questions about representations of real groups, and then the idea is to use Hodge theory to answer those questions. So let's see roughly how it works. So let me start with some sort of setup. So I'm going to take G sub R to be a real reductive Lie group. Okay, so if that's not something you think about every day, a real reductive Lie group is, by definition, for me, maybe a finite cover of some group bold G of R, where maybe bold G is allowed to be some connected reductive group over the real numbers. So something like if bold G is GLN, and this is just, I could take GLNR, or I could take maybe finite covers of GLNR, that sort of thing. And what we're interested in, various reasons, interested in representations. So studying continuous representations of this Lie group acting on topological vector spaces. The representations of GR, say on some sort of topological vector spaces. Although in practice, we'll talk mainly about algebraic models for these. Okay. So let me give you some examples of the sort of questions one might ask, kind of sample problems. Would be, for example, one of the big problems that people like to think about in this topic is classifying, say, irreducible, let's say, unitary representations. So, of course, if you're a representation theorist, then the first thing maybe you want to do, if you're given some sort of group, is classify its irreducible representations. And because we're in some sort of analytic category, maybe we want to impose some conditions on what sort of an analytic structure that this representation should have. So one of the most obvious things you could ask is maybe you have a Hilbert space with your group acting by unitary operators, and you should ask maybe to classify those things. And that turns out to be an open problem for really probably the majority of these real groups. Another thing maybe you could ask is to describe the structure of representations. So maybe you can write a list, but it's sort of an extra question to ask what the things on the list really look like. So one of the sort of standard sort of buzzword phrases you can put here is something called the orbit method, which is this idea that goes back to Kostant and Kirillov, that you should expect to find unitary representations are quantizations in some sense, which if timing is our friend, maybe I'll say in what sense towards the end, of something classical, say, okay. Classical thing is something called coadjoint orbits. So that's some statement that some theory that if you could sort it out, you would get information about not just lists, but structure of unitary representations. And then, maybe you want to describe, if you want to be really fancy, maybe you could try and describe the category. So not just the representations themselves, but how they relate to each other. So sort of buzzword that fits into this kind of general problem would be something like various kinds of categorical Langlands for real groups. Okay. So that's the sort of just, I suppose, a sketch of the sort of questions one might like to answer in the subject.
What if we ask for finite dimensional? Would they just come from the algebraic group or?
Yeah, so for finite dimensional, they more or less come from the algebraic group. If I assume there's a little subtlety that this group could be disconnected, so then, okay, there's a component group issue. But yes, if I say finite dimensional, then I'm essentially asking some question about finite representations of the Lie algebra. Finite dimensional, I really should say I probably want to do all these with complex coefficients. Of course, if I have a real reductive Lie algebra, finite dimensional complex representations, just representations of that complexified Lie algebra. And we sort of know that those are the same as representations of compact group or something. So they don't really care about the real form. So the interest in this is really in infinite dimensional representations, which, because these groups need not be compact, they can certainly have interesting infinite dimensional irreducible representations. Okay, any other questions about the general story?
Should I keep an example in mind through the talk? Like, what's a representative example?
Yeah, so a representative example, maybe I'm going to be speaking in sufficient abstraction that it won't matter so much, but an example, at least of a G, your example could be something like, let's say, one of my favorite examples is GR, it's SL2R. So SL2R acts on R union infinity by Möbius transformations, and then I can look at a representation of that might be something like L2 of R union infinity for some appropriate measure. Maybe think of this as a circle and put a round metric or something on it. So that's an example of, this isn't quite irreducible, but it's only got sort of a couple of composition factors. So that's a good example of an infinite dimensional representation. All right. So that's somehow the main idea of this talk, which goes back to Schmid and Vilonen, is that we have these sorts of questions. A lot of these are quite difficult questions, but Schmid and Vilonen proposed that there's some additional structure in the picture that should help you answer these questions. So they proposed that there exists some sort of Hodge theory or theory of Hodge structures for representations of GR, which should help with such questions, especially these questions like about unitarity, these sorts of things. Okay, so let me explain a little bit about what that should mean. Okay, so more precisely, so I've been talking about so far about these topological representations of real groups, which are sort of what appear for you in nature. So something like, you have a space on which the group acts and you look at some function space on it. But somehow, if you think of your representations as something like, L2 of this space, because there are various other kinds of function spaces I could take on this same topological or same measure space, and maybe in some sense it doesn't really matter so much for the purpose of understanding the group action. It doesn't matter so much which function space I take. So there's this theory due to Harishchandra of what are called, now we call Harishchandra modules, that sort of give you just some algebraic models for this, which kind of throw away some of these questions about which class of functions you care about. So more precisely, I'm going to model GR representations as what we call these GK modules. So here G is just the Lie algebra. So as observed, there's some important connection to Lie algebra representations. So I'm going to take the Lie algebra of my group and, well, I'm talking about complex representations, so I may as well complexify that. And then this K, so this K is going to be, again, the complexification of something real. The real thing is going to be just a maximal compact subgroup inside my Lie group. Okay, so you can think of this K as just some complex reductive group, maybe disconnected if the group that I started with was disconnected. Okay, so Harishchandra has this wonderful theory that says if I have one of these GR representations, then it has some sort of algebraic skeleton, which maybe doesn't quite have an action of GR, but has an action, still sort of an infinitesimal action of the Lie algebra, and retains an action of the compact part. So for instance, if I look at this L2 of R union infinity, this is R union infinity as a circle. L2 functions on a circle are Fourier series of some kind. And then the GK module is something like just finite Fourier polynomials inside Fourier series. Okay, so from now on, if you like, you can throw away the Lie group and just think about this pair G and K. And now I'm purely in some world of algebra. Okay. All right, so really this Hodge theory is for GK modules. And then what we would want, so you want a category, let's say mixed Hodge module over GK, some sort of category of mixed Hodge GK modules with some structure. So such that, maybe this should be some abelian category. So what sort of thing would I like to have a theory of Hodge structures on these things? So one, this should be, if I have some theory of Hodge structures, I should be able to tensor with, mixed Hodge structures. For me, because this world is kind of complex coefficient, when I say any sort of mixed classical Hodge theoretic thing, I'm going to mean the version with C coefficients. So a mixed Hodge structure, for me, is going to be the category of complex mixed Hodge structures. So here I'm going to take a vector space. This is just a C vector space. I'm going to take a weight filtration, a Hodge filtration, and then if I were doing something like real mixed Hodge structures or Q mixed Hodge structures, I'd put a Q or R structure on this V, and then impose some condition on W, F, and its complex conjugate. If I want to do a C coefficient version of that theory, rather than specifying a real structure and conjugating the filtration, I just specify a third filtration that need not a priori have anything to do with this one, but which just is part of the data. And then I impose that on each graded piece of the weight filtration, I should get a Hodge decomposition. So W n V is direct sum over P plus Q is n of FP for W and V intersect F bar Q for W and V. Okay. All right, so this should sort of be the kind of ambient category that acts on this thing. What else should I have? I should have a theory of pure objects. So pure objects plus weight filtrations. As one has abstractly, say, in the theory of mixed Hodge structures, you have a notion of pure Hodge structure, and by construction, every object is filtered by these pure things. So we should have that here. You should have some actual relation to GK modules. So you should have some forgetful functor, let's say an exact faithful functor from mixed Hodge modules over GK into, let's say, some category. So here I'm just going to take the category of finite length GK modules plus what's called a good filtration. Let's say V is my GK module, FV can be my good filtration. So good filtration just means V is a module over G and K. And I want the filtration should be invariant under K. And it should satisfy, so FV invariant under K. And if I have a module over a Lie algebra, this is also a module over its universal enveloping algebra. And so the universal enveloping algebra has this PBW filtration. So I just take elements of my Lie algebra, multiply them together, and I can filter by how many elements I need to take. And so you want this condition that somehow this filtration should be compatible with the filtration on U of G. And good means it's also finitely generated with this property. So some condition like this. And this thing here is going to be the Hodge filtration in this forgetful thing. So if I go object the image of the filtration on the object in the image is the Hodge filtration. Okay, what else would I like? So is it clear what this is saying?
Is your MHS, does it only have finite dimensional vector spaces there? Or?
Yes, finite dimensional. Yeah. Whereas this V is generally going to be infinite dimensional, but finitely generated over the coefficient.
Right. Because you were finite, I was curious.
Yeah. Yes, that's right. So I don't want for now infinite things. Thanks.
Is there a good model example of what this Hodge filtration is?
That's a good question. Maybe let me defer that question. I'll come back to it when I explain how to construct the theory.
Sorry, so it's not going to V comma F, it's going to U of G applied to V comma F or something?
No, what are you?
Dimensional, is it Harshchandra module? What is it?
So, sorry?
Is V on the right, is that a Harshchandra module?
Yeah. So I'm going to, maybe this is some poor notation. I'm going to use the same notation for the mixed Hodge module as for the underlying GK module. And then I will write F of that for Hodge filtration. So this is a fancy way of saying the object of mixed Hodge module GK have an underlying GK module which is equipped with a Hodge filtration.
So V is a generating set for Harshchandra?
Now V is just going to be a Harshchandra module. Maybe I should write this. That makes it clearer. So I maybe so object. Okay. So
Yeah, the finite dimensionality was in the mixed Hodge.
yeah, that's right. This V is not that V. Maybe I should call this one H or something. Make it less confusing. Yeah, thanks. Good. Right, yes. So these ones will be infinite dimension. Okay. All right. What else should I have? I should have some objects in here. So I'm going to impose that every irreducible GK module should lift, well, under some condition, which I invite you to completely ignore for the rest of this talk. So every irreducible GK module with what's called real infinitesimal character, if you know what it means, great. If you don't, ignore it. Should lift essentially uniquely to an object in here, maybe uniquely up to tensor with a one-dimensional mixed Hodge structure.
What's the filtration?
Well, that's a good question. So the claim here is that if I have an irreducible GK module with real infinitesimal character, then it lifts up to here. So in particular, there is some canonical filtration on it.
Okay.
So there is some canonical filtration, which is sort of the main player in the game.
And you'll give us an example of that.
I will give you an example. one. So the spoiler is this is going to be constructed geometrically from the corresponding geometric category, and I'll give you an example in terms of the geometry. Okay.
Can you say why Schmid and Vilonen thought this should exist? What made them think, oh, that there should be Hodge structures on these representations?
So the reason, well, let me defer this until just a couple of minutes. So the reason is, of course, they didn't just say, oh, there should be some theory with all of these properties. In fact, they probably don't even quite list these properties. This is partly semi-revisionist. I think this is sort of what was in their brains. But what they actually said was, okay, here's a construction of some objects and some categories. It should have some properties that would imply this. Okay, so there's a little more to the construction. But let me just finish my list of nice things that I should have. Okay, so this so far gives you some additional structure, some additional filtration, basically, on your objects, maybe with some nice sort of Hodge theoretic flavor. Now I'm advertising this as having something to do with unitary representations, something to do with Hermitian forms and so on. So there should be a theory of Hermitian forms here. So there should be some notion of polarization on the pure objects. So in Hodge theory, you have this notion of polarization on a pure Hodge structure. So similarly, you should have a polarization here. And what these polarizations should be here in this context, these should be some Hermitian forms on decay modules. Maybe invariant in some sense. Okay, there's a particular notion of invariance you want to impose, which I'll slightly brush under the rug. So if you have one of these complex pairs, if I want to talk about an invariant Hermitian form, I need to give some sort of real structure on this. And so, okay, there's some particular real structure you should take. Maybe it's not the one that we started with some sign, some kind of Hodge theoretic sign normalization. Okay, so that should exist. And then, okay.
The sign is referring to, where's the sign?
So the sign is, okay. If I have, so a standard example of a pure object is going to be one of these irreducibles. So irreducibles have no subtle quotients. So if I have a theory of weights, the weight filtration had better be trivial. So in that case, if I say I want an invariant Hermitian form, there's exactly one real dimensional vector space of these. So up to multiplying by a positive scalar, there's two choices. And the claim is that in the theory of polarizations on pure Hodge structures, you have a signature condition that I'll write down in a moment. In fact, let me say it now, and then it'll be clearer. So the polarization should have the following property. So polarized objects Vs, maybe let me even put in the Hodge filtration. These should be polarized Hodge structures in the following sense. I.e., I want V to decompose into, say, the weight is W. I should have a decomposition into pieces V, P, Q, where, let's say, F lower P, the F lower PV is direct sum over P prime, bigger than or equal to minus P, the VPW minus P. Okay, so the filtration should come from a decomposition, where this decomposition is orthogonal with respect to S, and S respected to VPQ is -1 to the Q definite. For all P. Okay, So in the theory of complex Hodge structures, one has this the sort of Hermitian forms that show up in Hodge theory. They don't tend to be positive definite, but they do have this sort of fun, this interesting sort of sign normalization. So for instance, Hodge-Riemann bilinear relations has this flavor that you have your Hodge decomposition and then your Hermitian form, it's not definite, but if you restrict it to one of the pieces, first of all, the decomposition is orthogonal. And if you restrict it to one of the pieces, it sort of has sign determined by the Hodge structure. So this is what you'd like sign normalization to mean. But I'm separating it out for the following reason. So the kind of meta theorem, let me just say this is a theorem. Is that there exists such a theory satisfying 1 to 5 and enough of 6 for applications. Let's say the unitarity questions. Okay. So well, you do have a theory satisfying all of these, conjecturally also this, but maybe not quite this. Some numerical shadow of it. What we can show is that in some sense this provides predictions for signatures of forms. You just forget maybe about the decomposition and just remember how many pluses and how many minuses you have, and we can prove those properties of signatures, but maybe not necessarily the decomposition. Okay.
Sorry, does 4 say that this exact faithful functor is more or less an equivalence?
No, I mean, it says that it's surjective on, modulo this, let's ignore this condition on real infinitesimal character. It says it's a functor which is surjective on irreducible objects. But, of course, again, maybe if I forget all the way to GK, Harishon to GK Voth. But it doesn't say that, right, maybe if I have an extension of objects. So one, of course, the uniqueness is not quite. You don't quite have uniqueness. It's up to tensoring with something. So there's some sort of graded lift thing. And also extensions may not necessarily lift.
But it's exact.
Yeah, but that doesn't mean that any extension in the image is actually the image of an extension.
Okay. So it can be killing something.
So, and a good example to have in mind is the forgetful functor from mixed Hodge structures to vector spaces. That has this property, but it's definitely not an equivalence of categories. Thank you. Okay. Anything else? All right.
For unitary irreducibles, the filtration is all in 1 degree?
No, very much not. So the filtration, I didn't say it, but it has to be finitely generated over U of G. So if I have an infinite dimensional irreducible, of course, this definitely cannot be in only 1 degree. So the subtlety I see, because maybe you look at this alternating sign, I think that this is what you want.
Yeah.
The subtlety is, which is what I brushed under the rug.
Okay.
For unitary things, you want invariant Hermitian forms under the real form that you started with, this GK. So GR and K are. For these polarizations, the subtlety is you take the Lie algebra of a compact form of G always, whether or not your original group was compact. So you have to do a sort of tweak of the signs to get the actual invariant Hermitian form, and that flips all of these minus signs. It's a good question. Okay. So maybe we should take the finite dimensional representations. These do have Hodge filtration all in 1 degree. Okay, so now the kind of plan for whatever time I have left, which is probably overly optimistic, is to tell you something about the construction, and hopefully everyone will feel happier when we're doing the construction because it'll be more geometry than what this has been. I want to tell you something about the proofs, and that's probably going to be all that we have time for. But if for some reason I go extremely fast, maybe then I could tell you something about these applications. Okay. although. So maybe for now, just accept there exist very interesting applications to these sorts of questions that I put on the board at the beginning. Maybe we can just talk about the techniques.
In this situation, so prefer modern applications, but
Oh. Well, maybe we can have a vote when we get to once we've done the construction.
Sir, I guess usually mixed Hodge modules are defined like over some base. Is the base here should I think of as a point or?
Well, let me answer that question right now. Okay, so the construction, indeed, as you might guess from the language, is to define this category in terms of some existing geometric theory of mixed Hodge modules on varieties. So that kind of idea, and this is why Schmid and Vilonen thought that this theory should exist, because they actually pointed out what the construction should be. So the idea, which is used Schmid and Vilonen, is to use mixed Hodge modules on some variety, on a complex variety, to construct this. Okay. So now let's introduce the variety. So let write G without the R, or depending on which category you prefer to work in, analytic or algebraic, it's either the complex points of my real reductive group, my reductive group over R, or if you like, it's just that real reductive group over R base changed to C. So this is just going to be a complex reductive group, however you like to think of such things. So if I had started with SL2R, then here I get SL2C. Okay, we're going to let curly B, so this is the variety we're actually looking at. It's going to be the flag variety of this complex group G. So this, shouldn't have curly brackets. So this you can think of as, maybe the easiest way to say it is G mod B, where B is the Borel subgroup. So if G is GLN, this is just the variety of complete flags inside CVN. G is SL2, it's CP1. Okay. All right, and then I'm going to be interested in the ring. The ring in question is going to be the sheaf of differential operators in whichever category you prefer to work in on this variety B. Okay. So the starting point for how you connect, so the aim is to connect modules over this sheaf of differential operators to our representation theory. And so this is accomplished by this kind of remarkably simple theorem, also remarkably powerful, of Baylinson and Bernstein. So the theorem maybe has two parts. So one, let's just first of all try to get a handle on what the sheaf of differential operators looks like. And one way to do that is ask, what ring do I get if I take its global sections? So one thing about this flag variety, so you can see from the presentation as a quotient, it's homogeneous under the group. So the group is acting on the left by multiplication. So when I have an action of a group on a variety, of course I get a map from the Lie algebra of that group into vector fields on the variety. And then if I take universal enveloping algebras, I get a map from the universal enveloping algebra into differential operators. So this is naturally has a map, at least from U of G. That's my universal enveloping algebra. And Baylinson and Bernstein tell you exactly what it is. It's in fact, this map is surjective. And it's a quotient by the center acting by a particular character. So I_triv is going to be just the action of the center of U of G on the trivial representation. Okay, so if you just force the center of this, whatever the center of this is, to act by this thing, I get this. So maybe, as a first approximation, maybe think global sections of differential operators is U of G. So they prove that. And then they also prove that, this is kind of the cool bit, so if I have any quasi-coherent sheaf of modules over this flag variety B, then I know that the higher cohomology of them is going to vanish. And I know that M is globally generated, either as a D module or an O module. Those two turn out to be equivalent. Okay. So maybe if you stare at this second part of the theorem for a moment and stare at it through sort of an algebraic geometry lens, you should maybe recognize this as properties that quasi-coherent sheaves have on affine varieties, affine schemes. So for the same sort of reason, once I know these two facts, this actually implies that this global sections functor from D modules into modules over the global sections, which are basically just modules over the Lie algebra on which the center acts with some condition on how the center acts. So just think that this is modules over the Lie algebra. This is an equivalence of categories. Okay. And all right, maybe let me also squeeze in. There's also a version, I would write it below, but I don't think you can see it. So let me say there's also a version where you can put, similarly, you can put K covariance on your D module.
This like two had nothing to do with the group, right? Is this like a theorem for all Fano varieties or something?
No, it's definitely not true for all finite varieties. This is probably only true for partial flag varieties.
Oh,
I think are the only, so you have to be homogeneous for this to work, I believe. I don't. Certainly I don't know an example of another. The proof very much uses the symmetry of the variety. And I'll give you another similar theorem that also very much uses symmetry. Anyway, so this has, so there you can also add K on both sides. So K kind of comes along for the ride. So you can impose that your module is K covariant, whatever that means, and then you get to stick a K here as well. Okay. There's also a version of this where I don't need to put, I get to change this character to something else, and there I have to think about twisted D modules, but maybe let me, for simplicity, focus on this little piece of the category. All right. Okay, so now you can maybe guess if I want to give you a Hodge version of this category. Of course, I just need to give you a Hodge version of that category. And thankfully that already exists, so we can appeal to other people's work. So you set mixed Hodge modules over GK, and let's restrict to this piece to just be mixed Hodge modules covariant on the flag variety. Okay. And I should say, actually, from this point of view, maybe K is actually not really important. I can also do this just with G, although maybe some of these properties, this 4 is not true if I put G. Okay. Okay. All right, so maybe let me give you a little digression on what this is. The digression on mixed Hodge modules. So mixed Hodge modules was originally this it's kind of monumental work of Morihiko Saito, basically putting together all sorts of results on variations of Hodge structure and plus much of his own contributions to construct a sort of six functor formalism for Hodge theory. So an approach to Hodge theory that sort of works via some theory of sheaves and functoriality and so on. So Saito did six functor formalism for Hodge theory. It has many of these properties. I've said, but instead of talking about G, this sort of Lie algebra G and this universal enveloping algebra, you talk about the ring of differential operators and so on. Saito's theory actually he works with kind of Q Hodge structures, and the Q structures one can of course do all this. One can of course use the Q version of this, but maybe that's slightly irritating and doesn't quite fit into the framework I want. So there's a version which you can read about in this sort of work in progress of Sabat and Schnell. There's this mixed Hodge module project, which is a version with C coefficients, which sort of for primarily linguistic reasons is better for what we're doing here.
Does the Q version imply the C?
So in this context, certainly in the context with K, yes, I think. The issue with the so of course, so you start with a Q version with Q structures. You think, okay, I should get a version with C coefficients by extending scalars or something. And that more or less works. The only issue is when you look at, there are some, you can have complex variations of Hodge structure that don't come from anything over Q in general. And there are some technical issues in that. So for instance, if you have a variation of Hodge structure with Q structure, automatically sort of local monodromies have to be quasi-unipotent. And that introduces technical simplifications into the theory. Whereas an arbitrary C variation of Hodge structure need not have quasi-unipotent monodromy. There's some generalization required. In this setting, because we're looking at these K equivariant things, I mean, I guess if I want this real infinitesimal character, so here I'm talking about trivial infinitesimal character. If I want this real version, if it's real but not rational, technically you do have not something non-quasi-unipotent in your theory, but in a very, very mild way. So I think one can just sort of one doesn't really have to worry about it. But certainly if for trivial infinitesimal character or rational, dense inside real, one can just make do with this more naive idea of starting with Saito and extending scalars.
Unitary representations, you care about the rational thing.
Exactly. So the rational thing is sufficient for unitary representations by some continuity arguments. So you don't really need this. But the language the way they describe the objects, which I'll show right now, is more convenient. But of course, it's just a rewriting of the same structures inside. So let's just see what the data of one of these objects is. So one of these mixed Hodge modules, so on X, so smooth variety over C, one of these mixed Hodge modules is going to be, so it should look a lot like our mixed Hodge structures over there, here. So it's going to be, again, something like a vector space, but a vector space is replaced with a regular holonomic dx module. You can think, I like to think of this as like a connection with allowed singularities in some fairly flexible way. That should have a weight filtration, and it should have a Hodge filtration, which is again going to be a good filtration over dx now instead of u of g. Okay, so that's the Hodge filtration. And then you also want to put in a conjugate Hodge filtration. And there's a little subtlety in how you do the conjugate Hodge filtration, which the issue is if I have a variation of Hodge structure, the Hodge filtration is supposed to vary holomorphically, which so plays well with, D modules I'm supposed to think of as the holomorphic sections of some vector bundle, maybe. Whereas the conjugate Hodge filtration is supposed to vary anti-holomorphically. And so it's less obvious how you should package that in the world of D modules. So there's a way of doing it, maybe for the interest of time let me not really explain, but essentially you want to write down the complex conjugate D module. This turns out to be slightly irritating to do, but it's easier to write down the sort of conjugate dual Hodge module. So in practice, you can index it on the conjugate dual. So there's some sort of packaging of the conjugate one of F bar. All right, but I invite you to ignore it. Okay. So that's sort of what it is, and then you impose various conditions. So you have many conditions, which somehow the way I think of where the conditions come from is you sort of start off believing that the theory exists, and then you think, okay, I want there to be a theory with all of these functors. How should I think carefully and cleverly about how you should define the functors, and then realize you need to assume various things for those functors to be well defined. So then make those various things be conditions, and then impose inductively that whatever the functors spit out should also satisfy those conditions, and so on. So it's sort of a somewhat horrible definition, but
And I'm not familiar with this at all, but let's say I just have a family of smooth projective varieties. Then is it like I'm wondering where's this D module? Is it what do they call that thing? The Gauss-Menin connection?
yes, exactly. So an example, for example, if I have a family of smooth projective varieties, the Gauss-Menin connection is my D module. The wave filtration is just trivial because the things should be pure. The Hodge filtration is the Hodge filtration. And then, that's however you get the complex conjugate Hodge filtration in that setting. And in general, if I have an example of an object, although this is a non-trivial theorem given how the theory is defined, is if I have any polarizable variation of Hodge structure, that will be an example of such an object. Although, the way that the theory is defined, that of course requires you to prove very non-trivial facts about how such things can degenerate. You have to appeal to Schmidt's nilpotent orbit theorem and this sort of thing to prove that those are examples. Okay. All right, so now let me go back to the flag variety for a moment. So if I go back to the flag variety, I want to show that this definition that I've made up here is a good one for the conditions that I've just erased. So a lot of those conditions actually follow immediately from how Saito sets things up. But one that doesn't, which I probably should not have erased, is that if I look at the forgetful functor from this category to filtered GK modules, which is some global sections functor, that should be exact in the filtered setting. So what I want, so I sort of maybe should have emphasized this more, but remember let me say this, so you want, with this definition, maybe just say this. That's even so that's even to the version, I guess, a bit okay there. So you would like that this functor, which sends M to M, or global sections of M and global sections of the filtration on M, you would like this to be exact. In the sense that this is an exact category here, and so exact sequences here should go to strict exact sequences here. So you know that's true before you apply gamma, and so you'd like to say it's true after you apply gamma, and you'd like to say that's because this theorem tells you cohomologies vanish. Except that this theorem only tells you that cohomologies vanish for an entire D module. They don't tell you that they vanish for pieces of a D module. And so you need a theorem, an additional theorem. Okay, so here is sort of in some sense, one of the workhorse theorems in this theory is that there's some version of this thing. So what you need.
You don't get it out of some semi-continuity theorem, they would just jump, but the whole sum is constant.
No, definitely not. So I'll explain, maybe let me state the theorem and then I'll explain why it's not obvious. So the theorem is that these two properties also hold for Hodge filtrations. Let M be a mixed Hodge mod mod B. Then I know that the condition is that the higher cohomology of each piece of the Hodge filtration is 0, I bigger than 0, or P. And okay, maybe this one is actually enough to get this, but in practice, it's also useful to know the following, that each piece of the Hodge filtration is globally generated. Okay, so why is this not obvious? Maybe we also answer that question while also answering the question that I deferred about giving an example. Okay, so let me give you the example which I said was my running example, in fact. So let's take my M. So I'm just going to assert that the D module that corresponds to that example of L2 functions on S1 is, so that in that case, my group is SL2R, my flag variety, so my complex group is SL2C, my flag variety is P1. So I want to write down a D module on P1. I'm just going to take the trivial connection, but allow sections with poles at 0 or infinity. Okay, so that's an example. And you can see this does indeed have vanishing higher cohomology. In this case, for stupid reasons, because it tracks some direct image of something from something affine. So that turns out to be, if you take maybe one way to see, if I take global sections of this, they'll get Laurent polynomials. Laurent polynomials look a lot like finite Fourier polynomials. Connection to the previous example. This is related to L2 of union infinity. Okay, so what's the Hodge filtration? So the Hodge filtration is this thing. So Fp of M is going to be, it's 0 if P is less than 0 for some choice of Hodge lift. So I can shift this filtration and still get valid answers. And otherwise it's going to be OP1 of, I guess I want to allow a pole of order at most P plus 1. Okay, so that turns out to be the answer. So there's some canonical filtration, okay, this is what it is. So some sort of pole order filtration. And in general, that's roughly true. But it's something like measuring orders of poles at the singularities of your D module, whatever they are. Okay, so this one you can check that because of this formula is only true when P is at least 0. There, this is I have O and infinity, so this is always a positive degree line bundle, so it does have vanishing high cohomology. But there's no particular reason why this had to be the formula for filtration in general. I could write down a different filtration where I start at P is -5 or something, and then you still use this formula. That would also be a perfectly valid filtration, it's just not the Hodge filtration. And for that, you'd have some negative line bundles in here, which would not have vanishing high cohomology, even though the union does.
So does this thing, suppose I'm just trying to have a picture of this internal to the representation theory. Suppose I didn't know about it. So for example, if I took a representation of SL3, do you have a picture of this in terms of the K types?
That's a good question. I mean, sort of no. So it doesn't just depend on K types. Right? So it depends very much also on infinitesimal character. So for instance, if I look at a principal series representation, I can, this is a series, so I have a continuous parameter. Then what happens is when my parameter is sort of very small, the Hodge filtration is sort of nicely spread out in some sense. But when it gets large, kind of the low, everything, as you increase the parameter more and more, everything is going to start trying to kind of move down. And eventually this lowest piece kind of gets bigger and bigger and bigger and eats everything off. So this has actually already started to happen in this example. So if you look at it, the global sections, there's one, K is in this case C star, there's one, each K type has one dimensional multiplicity. There's F0, which is the smallest piece, negative gamma M. This is three-dimensional. And then as you increase, you just add one K type at a time. So this is already, in some sense, not the zero in the theory. The zero in the theory is
But
type of unitary inductive.
the smallest p's have some vague relation to the smallest K types.
Some vague relation, yeah. That's
Okay.
right.
And is there a way to, you said this is canonical in what sense?
Well, in the sense that there's a construction you can make and up to a shift of the filtration.
But for example, can you wrote, is your theory the unique one? Characterized by some list similar to what you said?
I think no. I don't think in any obvious. I mean, I don't know an example of another one, but I don't see any particular reason why what I said is sufficient to characterize the theory.
And mine are different. But do you think? I guess do you think this filtration is somehow real? Would be independent of.
I think the things that I wrote down are not sufficient to be axioms for this.
Okay.
But this is sort of the way this behaves is it's clear enough that this is the sort of the right object to study.
What is the weight filtration on this guy?
So in this case, the weight filtration question. So this has a sub, of course, which is O. So I guess I want to index it so that. So I want to start it at 1. So this is going to be OP1. And then W2 of M. The W0 of M is 0. And W2 of M is the whole thing. Okay. That's the weight filtration.
So the sort of discrete series pieces are in weight 2.
That's right, yes. Okay. So we have a couple of minutes left, and I have maybe 2 sections to cover. So okay, I said there would be a vote. Does anyone want to see ideas of proof or application? Okay, so we've got some votes for applications and no votes for ideas of proof. Good. All right, so let's do applications. And thankfully, I have only enough time to advertise, which is, of course, easier than actually explaining things. All right, so let's do some applications. Okay, and the idea is somehow, well, yeah, let's do some applications. So the applications somehow fall into, there are 2 ways you can exploit the structure to get interesting results that we've found so far. And one is to take what I sort of think of as lowest piece phenomena. So that's where you look at this, Hodge filtration. Okay, you've constructed some huge theory, it gives you some filtration that's mysterious. One thing you can extract from it is the lowest piece, so the first non-zero piece of this. So here it's this 3-dimensional subspace. Okay, so here is this is sort of a cute application because it's something known. So this is Vogan's theory of lowest K types. This maybe partly answers to these questions about K types, size of K types versus size of Hodge filtration. So Vogan has this theory of if I take a representation, there's a sort of, you can look at its restriction to K and find sort of a smallest piece in some sense. And one of the amazing facts about this is if you restrict to tempered representations with real infinitesimal character, okay, So that's some nice class. Then this lowest K-type map gives you a bijection between this and irreducible representations of K. Okay, so some irreducible representations of this just compact or reductive algebraic group of certain interesting representations of this thing, and something that sort of comes out of what we write in this proof of these theorems is that this map is V goes to F min of V. So the lowest piece of a tempered thing is just its lowest K-type. You can prove sort of work in something we're writing up at the moment is you can actually, so Vogan does this by some incredibly difficult combinatorics. The longer I look at the combinatorics, the more impressed I am that he managed to do this. Whereas with the Hodge theoretic machinery, you can prove this bijection with sort of only easy combinatorics. So that's something we're writing up at the moment. Or another thing you can do, maybe let me just squeeze this in. But you can also prove some bound on representation. So there's something called the FPP. What was a conjecture is now a theorem. Which basically is sort of a converse to this, maybe, where you just look at what the lowest piece tells you about unitarity, and that gives you some bound on how big unitary representations can be. And then the other thing you can do is you can calculate this associated graded, which is a coherent sheaf, say K equivariant, on maybe this is slightly too many symbols for this point of the talk, but if I take the associated graded of one of these GK modules, I'm going to get something which is naturally a coherent sheaf on G star. But in fact, because it's a GK module and there's further conditions, it actually lies on some subvariety inside G star, called the K-nilpotent variety. Okay, so here is a little theorem. So we can actually, in this tempered case, we can compute the associated graded. You also get something nice. Let me give you maybe something which is more, tells you something new. So if I have a sort of representation, it's called a small boundary unipotent, whatever that means. So then this associated graded of V is going to be just the direct image of some vector bundle on a K orbit inside here. Okay, which implies, so given that calculation, you can prove that V is also unitary. Okay, so this is a case, a kind of very important case, which is completely new, well, at least new in this generality of this orbit method. Okay, so I think I'm slightly over time, so let me finish this.
And would this help answer the unitarity statement of Arthur's conjectures for real groups?
Yeah, that's a good question. So this does overlap with that question. It doesn't give us a complete answer. It does tell us, so one thing you can use this to prove, the corollary of this statement is at least the Arthur, right, this certainly implies the Arthur unitarity for complex groups.
Okay.
So that's at least getting somewhere towards real groups. So right, what is the issue somehow? You would like to say that so Arthur unitarity gives you some collection of maybe unipotent packets, and they are very closely related to this condition, except they need not satisfy this small boundary condition. So somehow for this theorem to be possibly even plausible, you need the inclusion of this into whatever this is to have the boundary should have codimension at least 2 so that this is coherent. That thing has to be coherent. And for complex groups, the boundaries of nilpotent orbits do have codimension at least 2. So this works fine, and you get this. But for real groups, sometimes they do and sometimes they don't. So this was only give some cases of Arthur's unitarity, but not in general.
Do you know whether there's a series of like mixed Hodge modules on formal schemes?
That's a good question. Certainly not written down.
Okay.
The issue is mixed Hodge modules is really constructed as sort of using complex analysis. So it's an analytic theory. So for formal schemes, you could probably, so maybe one could try, I don't know whether this works, but one could try to say something like choose some complex analytic model for your formal scheme, if you can, and then take mixed Hodge modules on that, and then maybe show, at least in some germ sense, that this doesn't depend.
Yeah, but mixed Hodge modules, like they depend on the algebraic structure of the variety, right? Like if the variety has.
So that's a good point.
Algebraic.
Yeah, so there is a theory of mixed Hodge modules on complex analytic things, analytic spaces. At least, complex manifolds, let's say. So there's actually two. What you do is you first you can construct 2 versions of the theory. One which is purely complex analytic, and one which is algebraic. The algebraic one still uses the complex analytic one, but it's got fewer objects. And so a lot of the things still do work for the complex analytic thing. You just don't necessarily have all the functors, which is already an issue for D modules and holomorphic maps.
Okay. Yeah. So
but possibly one could.
The reason I'm asking this is that it seems that this GK module can be sold as a representation of a formal a group formal scheme.
Yes, that's true.
Yeah. So maybe you can use descent to do this, or if there's a series for formal schemes.
Maybe. Yeah, I think it's certainly maybe, but certainly you will need to input some analysis somewhere. Because you certainly can't do this completely algebraically. So, yeah, I don't know.
What do these things say anything about like possible extensions between GK modules that are anything useful about possible extensions between GK modules?
That's a very good question. So if you want to compute X groups between GK modules, so one thing you can do, so this is sort of, to some extent, work in progress, but if you look at, so here is some connection to that problem. So you do have some functor that goes from, I've got this functor that goes from this thing. And maybe even, since we're talking about extensions, but derived categories here. So I do have some functor like this. And maybe not quite true, maybe you have to pass to the resolution, but there's sort of a conjecture approximately that this should be, so this is, there's a Kovernikov which approximately says this is fully faithful. So we do expect, and I'm working on some proofs of this statement, that you can at least compute X between GK modules in terms of coherent sheaves on top.
Okay.
And then, okay, maybe you've got more room to move and things. So for instance, like this, I alluded at the start that one wants to use this sort of tool to describe categories of representations. But this would be one way you can try to do this, exploiting the Hodge structure to kind of put yourself in some other world where you can do things like restrict to constant slices and there's more geometry available here for computing these edges.
Because like if you have some principal series induced from maybe a discrete series on a smaller group, parabolically induced, then sometimes if the infinitesimal character is large, you get all these different extensions that are interesting. And I wonder if like the theory can say anything about what they are.
Yeah, that's a good question. I mean, of course, you can see that so there's already a lot you can get out of just Valence and Bernstein. Okay. So Valence and Bernstein can, in principle, you can encode those questions in here. So there, of course, you've moved varying the infinitesimal characters. So you have some parameter here. And there, I mean, I guess you see those sorts of X coming from the fact that you've got this extra X maybe comes from, there's a lot you can get out of looking at the theory of intertwining functors here. You know what that means? Intertwining functors. So it's related to intertwining operators.
Okay, that was going to be my other question. What is the relation to the intertwining operators?
Yeah, so there's a whole story. I mean, this is maybe a slightly long story that I avoided talking about. So I said if you want to vary the infinitesimal character, you have to put a twist here, which you can then vary. The match from twists to infinitesimal characters is not one-to-one, though. The file group covering. And so you get, and for at least generic infinitesimal character, you get, these will all be equivalences. And so there are functors that kind of move you around between the different twists here. So those are the intertwining functors. And so you can get a lot of information about the X between modules here by looking at the modules here plus the intertwining functors applied to them.
And can you relate these intertwining functors to like integral intertwining operators in the sense of?
I maybe don't want to try and make a precise formulation now, but yes, they're sort of related. I think this is why Valence and Bernstein call them intertwining operators. So for example, if I take a principal series, somehow this principal series construction naturally leads you to a D module. If I look at a principal series, at some parameter, and a principal series of the file group related to parameter, the intertwining functor sort of moves you to the same category, and then there's a sort of a morphism between the intertwining functor and the original thing, which is the intertwining operator. So they fit together.
Are there further questions? If not, then let's take this later.